Another scheduling algorithm that we will consider this lecture is round robin. Round robin is an algorithm that gives every process a time quantum, a time slice. It's usually between 10 milliseconds and 100 milliseconds. If the process finished execution within this time given to it, that's fine. If the process needs more time, it will be swapped to the end of the ready queue, and the process in the head of the ready queue will go into the ready queue, into the CPU. So that there is a timer that will interrupt the CPU if the process did not terminate before the time quantum finishes. If the time quantum was too long, it will just look like FIFO, first come, first served. And if the quantum was too small, that means there will be a lot of context switching, creating a lot of dispatcher latency and a lot of wasted time in overhead. So the length of the quantum is crucial for round robin to have a good performance. An example for round robin with quantum 4, we have three processes, P1, P2, P3. P1 needs 24 milliseconds, P2 3 milliseconds, P3 3 milliseconds. P1 will be allowed for 4 milliseconds. It will execute for 4 milliseconds. There will be 20 milliseconds remaining. P3 will go next. From the 4 milliseconds, it needs only 3. So it will terminate before its quantum is expired. Then P3 also needs 3 milliseconds, which is less than 4. It will terminate before the quantum expires. Then P1 will be allowed. It needs more 20 milliseconds. These are 5 quantums. It will be running for 5 continuous quantums until it finishes execution, because there are no other processes in the queue. Looking at these algorithms, the best performance usually goes to shortage of first because it has the smallest response time. And as we have said, in round robin, we have to take into consideration the context switch time. So we should choose the quantum wisely to minimize the overhead. As you can see here, if the process if process's average time is 10 milliseconds and the quantum is 12, if the whole thing will look like first come, first served. If we choose it in the range of 6, 5, that means we have one context switch time. If we choose it at 1 millisecond, that will create 9 context switch time. So you can actually estimate the average time a processes in your system runs, either using simulation or with actual observation, to choose the right quantum for your different processes in your system. The quantum also affects the turnaround time. The turnaround time is the running time and the waiting time together. As you can see, with the as the quantum increases, the waiting time decreases for a while, then it increases again, and then it goes flat. What you want to take into consideration that the average CPU burst time should always be larger than your quantum. In operating systems, ready queue is usually not implemented as a single queue. It's implemented as multi-level queues because there are different processes. At least there are foreground, which are interactive processes, and background, these are mainly batch processes. These two types of processes have different priorities because of their nature. An interactive process needs immediate response, where the batch process does not need an immediate response. So a process is assigned a queue. It's either a foreground or a background. Usually, the foreground queue is implemented in round robin. So every process will have a time quantum, a time slice, and the background process is first come, first served. It's non-preemptive. But foreground processes, the queue of the foreground has higher priority than the queue of the background. So all the processes in the first queue will be executing before any process in the second queue. Usually it will be like 80% of the CPU time will be assigned for the foreground process queue, and 20% of the CPU time will be assigned for the background queue. There might be more than 2 levels in our multi-level scheduling, queue scheduling. As we see here, we have system processes with the higher priority, interactive processes, next priority, interactive editing processes in the third level, batch processes in the fourth level, and student processes last. So the lowest priority will not, a process of a lower priority will not get a chance to execute unless all the other queues are actually empty. This will create serious starvation. That's why a multi-level queue scheduling with feedback was introduced, where a process will move between various queues from a lower priority queue to a higher priority queue after waiting for a certain amount of time. It's just like aging, but here aging will increase the priority with moving a process from one queue of a lower priority to another queue with a higher priority. An example of this is here. As you can see, we have 3 levels. The first is implemented in round robin with quantum 8. The second is implemented in round robin in quantum 16. The third is implemented in first come, first served. That means processes in the last level with the lower priority, if given a chance in the CPU, they will run uninterrupted until they finish. But they won't be allowed in the CPU unless the 2 other queues are empty. What if the process was taking for too long in the last queue? After a certain amount of time, it will be allowed to move to the upper level, upping its priority and lowering the amount of time it is allowed in the CPU. If the process stayed in the second level long enough and it wasn't able to get into the CPU, it will be allowed to be in the it will be allowed to move to the higher priority queue. So it will get shorter amount of time, but it will be allowed in the CPU. As I've said, the rest of the chapter is up to you if you go and read it, and I really recommend that, but it's not a part of our course this year. Thank you.